Hello, everybody. I'm just waiting for my colleague, Ms. Piret Larsen.
Hello. Are we all ready and set to start?
Yes, I think we can start now.
Yeah. Okay, so the time is here to start with the session number 2 in our webinar seminars. And today's topic is energy analysis of balanced ventilation system. And we are focusing on heat recovery, cold recovery, and ventilative cooling. Today we are 2 of us in front of you. My name is Piret, and I work in Sales International as Business Development Manager. And this is one of my first presentations in my new role. And luckily, I have my colleague Adrian. So we will do this presentation together.
Thank you, Piret. My name is Adrian. I'm working as a technical project engineer at Zehnder Sales International. I'm hosting you from the Zehnder Academy in Germany. Some of you already know me from the first webinar where we talked about a comfortable and healthy indoor climate. Today we dive into the energy of balanced systems. So I'm happy to have you here. Yeah, I'm looking. Let's get started, Piret.
Indeed. But before we get started, then there is also this almighty famous question that from where are our listeners from? From which side of the world? Do we have international audience today, or we are focusing on one country? If you can answer to the chat version, then we would also know if we should say good afternoon or good evening. But I think we can start also with the topic of today, and that's why people are or have joined us today.
Yeah, we got some answers. We have attendees from Romania, from Germany, of course, from California, US.
Ooh. Then it's
from
already
India. Yeah.
even. Okay, but then let's start. Question for our today's session is that how much energy is saved by a balanced ventilation system compared to ventilation via window? So that's something that we want to provide you with an answer and with the explanation and with some examples that why ventilation is important and how we could benefit from it. And we start with bringing you, if you could also write an answer what you think about how much energy is saved by balanced ventilation, then please select one of the options that are presented in the display. And in the end, we can see that how many right answers did we get.
Yeah, so round about 60% say we can save 90%, 30% say 50%, and 10% say 20% energy savings.
Okay, very good. Thank
and
you.
I can also see that 90% of the attendees voted. So I think we will close the session now. And at the end of our presentation, we will answer this question.
Yeah, thank you for everybody who participated and who gave their votes. Let's go through the presentations and then we will see what's the answer. Also, the background for this presentation and for about our ventilation systems at all is that we want to turn the attention and the focus on that how ventilation plays a major role in current and future buildings, because the regulations are getting more strict and we are building more insulated buildings, and tight building envelope and air tightness is very important. And for energy efficient in building technologies and industry is very important, but we still cannot forget any aspects on the comfort of the health of the people. And besides or after the well-being and comfort, energy benefits are very important, so we could focus on savings and also for the resources that we should not spend them too much, because for example in the colder areas around 40% of the total energy is used to heating for the houses, and this is too much. Also, where we want to turn the focus and explain a little bit more is the understanding of ventilative cooling in the balanced ventilation systems, and also that we should focus while we're thinking about ventilation, the system approach, that we do not ventilate only in the summertime or in the winter time, but there should be a solution that will take the best of the annual ventilation that would be needed, and we are taking care of all the seasons. And also to shift from focus of heat recovery to overall benefits for all climates, and to think about the global warming and urbanization and how this is also affecting the ventilation need. The main targets for today, for the session 2, is that hopefully in the end of this presentation, we will be able to answer and we have information about how much does balanced ventilation save on the heating load of the house, how much does balanced ventilation save on the cooling load of the house, how much ventilative cooling is brought by a balanced ventilation system, can we prove that from the results of field studies, and also that how much electrical energy is needed for the above benefits. And saying that, then Adrian, how much energy we could save by balanced ventilation if we compare it to ventilation via windows? Could you give us a little inside information about that?
Yeah, of course. Thank you, Piret. Yeah, before I come to the answers of these questions, I want to give you a short overview about how we want to approach these answers. At the beginning, I will introduce you in our ventilation units. So we will talk a little bit about the technology, and I will also show you different installation types. Then we move on to the field study. We will see where the units are located, which units were used for the field test, and which parameters has been monitored. And then I will go a little bit into thermodynamics to see the potential energy savings in theory. So I will explain different modes of balanced ventilation systems based on graphics. So we will talk about heat recovery, and on the other side, we will talk about cold recovery. We see how the bypass activation works, and we will also talk about our ground heat exchanger, which provides energy savings using renewable energies. At the end, we will come to the most interesting part. We will show you the results from the field study. So we will point out how much heat was recovered and how much cold was recovered. We also will see how much energy or coolness was brought by ventilative cooling. And we will also take a look at the power consumption, which is mainly the power consumption of the fans. And therefore, we will at the input versus the output to get the performance and the energy efficiency of our ventilation systems. So yeah, let's begin with the ventilation unit. Today we are talking about balanced ventilation systems for residential housings. Different units in our portfolio, starting from small decentral applications like the comfort here with an air volume flow of 50 cubic meters per hour, up to central units with 600 cubic meters per hour. For the field studies, we use the central unit, the Comfort Air Q, which is available in 3 sizes, 350, 450, and 600 cubic meters per hour. And the heart of these units is a cross-counterflow heat exchanger with an energy efficiency of 90%. These units also come with an automatic modulating bypass and with integrated sensors to regulate the volume flows. Let's take a closer look at the heart of the unit. Our units come by default with a heat exchanger with an efficiency of 90%. It's a diamond heat exchanger, but we also have an enthalpy heat exchanger, which not only recovers the heat, but also humidity. So at the end, you have a slightly higher efficiency due to the recovery of sensible energy, which relates to temperature. And we also recover latent energy, which relates to humidity. So in total, we have a little bit higher efficiency. Yeah, I want to show you a short video now about our enthalpy exchanger, where they explain how it works and what benefits does it bring to us. One moment, please.
We spend 90% of our lives indoors. Our lives have become a complex mixture of commuting, indoor work, and indoor activities. To save energy, we have insulated our houses so well that the rooms do not get enough fresh air. Fresh air is obviously best for our health. On cold winter days, the air indoors is often too dry. This can lead to unpleasant irritations, dry skin, red eyes, or even health problems. On hot summer days, on the other hand, the warm, humid air feels even warmer than it actually is. Fresh air and relative humidity in a comfortable range between 40 and 60% are best for our well-being. The answer? A comfortable indoor ventilation system with humidity recovery. It enables optimal indoor air quality and is a healthy and energy-efficient alternative to opening windows. Zehnder's comfortable indoor ventilation system with enthalpy exchanger recovers up to 80% heat and additionally up to 70% of the humidity. So, In the winter, it retains heat and moisture inside a building whilst providing the right amount of fresh air. In summer, on the other hand, heat and humidity is extracted from the warm, humid outdoor air before the fresh air enters the house. Zehnder's patented polymembrane acts as a separating layer for the airflows. At the same time, it prevents transfer from impurities and odors from the extract to the supply airstream. This energy-efficient process prevents the indoor air being too dry in the winter and too humid in the summer. This gives you the best indoor air quality for even more comfort and well-being. You can feel it whenever you enter a room that's using Zehnder Comfortable Indoor Ventilation. You already have a Zehnder Comfortable Indoor Ventilation system and would like to extend it to humidity recovery? You can simply upgrade to the Zehnder Enthalpy Exchanger. Your Zehnder partner will be happy to advise you. Zehnder, always the best climate.
Yeah. So they mentioned a heat recovery rate of 80% and a moisture recovery rate of 70%. In total, this is more than 90% energy recovery. Another feature of our ventilation, the modulating bypass, that ensures that the right amount of energy is recovered at any time. Let me explain this with a short example. You can see it on the left-hand side. This could occur, for example, in autumn in our region. So we have a sunny day, we have 14 degrees outside. Inside we have 23 degrees due to internal gains and also to solar gains, so it's a little bit too warm. We would like to have 21 degrees, for example. So if we use now the full heat recovery, we will take in the air at a temperature of 22% because of the 90% efficiency. So from time to time it gets too warm, our house is getting overheated. So if we open the bypass completely, which is nothing else than just open the window, except the filters which we use in our ventilation units. So what you get then is a supply air on the same temperature level as the outside air. So then we would take in the air at a temperature of 14 degrees and it will be too cool. Now we developed the modulating bypass, which regulates the amount of heat recovery and the bypass. So we can mix up these two airflows and we take in the air at a temperature of 17 degrees. So that's the optimum temperature. And this is done by two flaps that cover the heat exchanger in a way to regulate the airflow going through the exchanger. So what we have here is a control of heat recovery to get an optimized supply air temperature. Another accessory is our subsoil heat exchanger. The subsoil heat exchanger gains energy from the ground, where a collector lies in a depth of up to 2 meters. And on the other side, we have the heat exchanger next to our unit, and a circulating brine brings the heat or the cold. In winter, when the outdoor temperature is low, we pre-temper the air and we prevent the unit from freezing with the help of the subsoil heat exchanger. And in summer, it lowers the temperature of the supply of the outdoor air, and air provides a comfortable supply air temperature. And here we also have energy savings due to the use of renewable energies. And we also need to understand the control of our units. And we have integrated sensors that are measuring the temperature and the humidity at the supply and extract air, as well as the exhaust and outdoor air. And we also have pressure sensors that measure the pressure after the fans. And with that measured values and an intelligent control strategy, we can regulate the air volume to provide a comfortable indoor climate. And there are also some optional strategies. If you look at the example on the left-hand side, so there the indoor humidity is high, and the unit detects that the outside humidity is lower. And then the unit will rise the volume flow to get out the humidity of the house. And yeah, same applies the other way around. And this also applies to temperatures. So whenever the unit detects there is a potential for cooling, for example, because the outdoor air is cooler than indoors and there's a need for cooling, the unit will increase the air volume flow to get in the coolness. Yeah, now you got some insights to our unit. You understand the technology behind it. So now we can move on to the field study and therefore to the energy analysis. Our colleague, Mr. Bart Kriemers from the Netherlands, implemented this field study. He has tested 3 ComfoRQ units, which were same in control and same in construction. They only differ in their size. And yeah, he also used different installation types. So we have 3 ComfoRQ units with a heat recovery, 2 ComfoRQ units with the enthalpy recovery, and 1 ComfoRQ unit with enthalpy recovery, and additionally the ground heat exchanger. These units were located in the Netherlands, in Germany, and in Austria. The monitoring period started in September 2016 and ended in August 2017. So we built up a whole year. The recording interval was 5 minutes, and he measured the temperatures and humidity of all air streams, the fan duty, the rotational speed of the fans, the airflow rates, and the total pressure. Yeah, so to understand the savings we can reach here, I would like to show you some graphics and point out the potential energy savings. Yeah, let us start with a ventilation unit without heat recovery. So what you have on the x-axis is the outdoor temperature, and on the vertical axis you have the indoor temperature. The black line shows the desired inside temperature, and the green line shows the supply air temperature. So what you can see here is, let me do a little example. If we have 0 degrees outside, we are here, and then we get in, the green line shows the supply air temperature. Of course, we get in supply air temperature at 0 degrees. And now we need to heat up the air to our desired level. So this amount here of energy needs to be provided by the central heating system. And the same applies in summer or in warmer regions. Here we need to cool down the air to get on our comfortable level. Now, what happens if we build in a heat recovery? There you can see the supply air temperature is very close to the desired air temperature due to the heat recovery. Let us do the same example, 0 degrees outside. And then we get it on a higher level due to the heat recovery. So what we have here, we have a, let's make it easy. We want to have an inside temperature of 20 degrees and we have an outside temperature of 0 degrees. So we have a temperature difference of 20 degrees. And now we have a heat recovery with an efficiency of 90%. So what we get is a supply air temperature at 18 degrees. So now the temperature gap is quite small. We just need to heat up the air about 2 degrees. And the same also applies in summer when we are using the cold recovery. Let's go a little bit further. Now we can see what happens if we use a modulating bypass. On the left-hand side, you can see the heat recovery. It's the same as before. On the right-hand side, you can see the cold recovery. It's also the same. Yeah, and now we take a look at the area in between. So let me start with the blue arrows. There we have a potential outside because the outdoor temperature is below the inside temperature and we have a need for cooling. So what we do is opening the bypass and get in the air. This is ventilative cooling, or you could also say free cooling. And then when we go a little bit further to the green area, this is the working range of the modulating bypass. So at lower temperatures, we have more heat recovery, less bypass activation, and at higher temperatures, we have more bypass activation and less heat recovery. Oh. The bypass is activated when all of the following conditions are true. So the central heating is not active, so that we do not have a waste of energy. And there's no risk of too cold supply air to prevent droughts and also to prevent condensation on the supply ducts. The outdoor air is cooler than the indoor air, so ventilative cooling is possible at all. And last but not least, the extract air is warmer than comfortable. So ventilative cooling is required. Yeah, now we have additionally a ground heat exchanger. And what you can see here at low temperatures, when we are minus degrees, and we are preheating the outdoor air to protect the unit from freezing. So we have a frost protection. When it's still cold but warmer than 0 degrees, we have a comfort increase because we are pre-tempering the outdoor air, so we get out a higher efficiency. And in summer, when it's warm outside, we are pre-cooling the air, and there we can make use out of ventilative cooling using our ground heat exchanger. So here we have also energy savings. So this was the theory, and now we take a look at the results from the field study. It's almost the same graphic. We have the outdoor temperature on the horizontal axis, and on the vertical axis, the inside temperature. The red dots are the value measured throughout the whole year in a 5-minute interval from the supply air. And the yellow dots show the extract air. So what we can see here, oh, sorry, this is the wrong graph. I just wanted to show you the monitor temperatures with heat recovery, but it's the same graphic. So what we can see here in winter, we are using the heat recovery and we get the supply air on a comfortable level. So here we save energy on the heating load of a house. When it gets warmer, we begin to open the bypass. So we have energy savings due to ventilative cooling, what you can see here, these red dots. And if we go further, we can see a change. The outdoor air is getting warmer than the inside air. So we switch back to the heat recovery, or I should rather say cold recovery. So here we recover cold and save energy on the cooling load of a house. So this is the same graphic with the ground heat exchanger. We can see a slightly more efficient heat recovery in winter. That's due to the pre-tempering of the outside air. But the bigger effect is the ventilative cooling. Firstly, we have ventilative cooling directly from the outside air. And when it gets warmer outside, we can still use the coolness of the ground to provide coolness for the house. So the brine pump is activated and brings coolness to the outdoor air. So the supply temperature is quite comfortable. And this is during the whole summer, as you can see. Yeah, before we come to the energy savings, I just want to explain shortly how the energy savings were calculated. This is done by the most known formula of building engineering. So we have for the heat recovery, the mass flow of the air times the specific heat capacity times the temperature difference between supply and outdoor air. The same applies for the cold recovery, and for ventilative cooling, we are taking the supply and the extract air into consideration because we do not use the heat recovery. So let's take a look at the monitored energy savings with the heat exchanger. So here we have on the horizontal axis the outdoor temperature, and on the vertical axis the heat recovery and the cold recovery, as well as the ventilative cooling in watt. So let's take a look what happens in winter. Here we have the highest heat recovery rates. This is due to the bigger temperature difference. So at lower temperatures, we get more energy savings, logically, yeah. And we can also see a dependence of the heat recovery with the air volume rate. The higher the air volume rate, the higher the heat recovery. And in summer, we can see this is also shown by the red dots. We can see the cold recovery. So here we are using the heat exchanger to get the cold from the extract air to the supply air. And the blue dots show the energy brought by ventilative cooling. This is the same graphic, but here it shows the energy savings with the ground heat exchanger. So what we can see here, in winter, it's almost the same. We are a little bit more efficient, but the bigger effect is in summer when we make use of ventilative cooling with the pre-cooling by ground. And what we can also see here is that we do not have cold recovery when we have a ground heat exchanger, because we use the ground heat exchanger and we will avoid the cold recovery. So we will avoid the heat exchanger. Yeah. So these were the energy savings, but now we also need to take a look at the energy we need to provide these systems, which is mainly the electrical consumption of the fans. Yeah, as you know, the electrical consumption of fans depends on the system duct resistance, and it also varies quadratic with the airflow rate. So in the diagram, we can see the yearly average airflow rate of the 6 field units and the total fan consumption. So we had 100 kilowatt hours per year up to 600 kilowatt hours per year in the Netherlands. So this was the highest rate. So since I am more into thermodynamics and not into electrics, I would like to hand over to Piret again. So Piret, could you please explain the audience if this is a huge amount of energy which needs to be provided, or whether this is marginal?
Yes, thank you, Adrian. As Adrian already demonstrated and showed the graphs and also, let's say, the values that has been measured in the real functioning systems in the real building sites, then we would also like to analyze the results and answer the question to Adrian about the quantity and the size of the energy that is used for the indoor climate, or to provide a good indoor climate. What was measured during this time was also the fan consumption, and if we are now looking for the annual heat recovered, the heat recovered as a thermal energy. And to provide a comparison, we can use similar calculation as it would be for the heat pumps, this coefficiency of performance, that we have the heat recovered, and we will divide it with the fan consumption and the electricity that was used to have it to provide this kind of a heat recovery. This we can call a seasonal performance factor for heat recovery. In those 6 real cases where we have measured and the real results, then the values are in the tables, the results are in the tables, and for that we have seasonal performance factor for heat recovery, SPF-HR, from 16 to 37. Usually for heat pumps, this is around, in good cases, 4 or 3. So, and if we have a higher number, that means that the, let's say, the work that is required is less, and therefore the costs are less. So in that way, to answer to Adrian, then this consumption of electricity is rather a margin amount in comparison to the recovered energy. But we also have to keep in mind that if we do those kind of comparisons and have overview of this data, then we need to think about the outdoor climate, because if we have a 5 degrees in outside and -5, there is difference. We also need to think about the flow settings and comfort settings. The seasonal performance factor or heat recovery, or the seasonal performance factor overall, is low when the flow settings, seasonal performance factor is higher when the flow settings are lower. Therefore, it is that we have more heat recovery area per cubic meter per hour, and also the fan consumption is the electricity for fan consumption is lower, therefore the value will be higher. But overall, when we think about the annual costs and savings and energy efficiency, then with this heat recovered ventilation, we are definitely adding value to the overall system. Now let's move to annual cold recovered. Here, the main principles are similar like they were for heat recovered. Then we have seasonal performance factor for cold recovered. Same way, the cold that we have recovered is divided with the electricity consumption in cold recovery season. So it's also that we cannot take these values when we have to heat, or vice versa. For heat recovery, we will not consider cooling because this is not reasonable to do one or the other in the different season times. For cooling, then in the same values were measured in the sample cases that we had in Central Europe. And then also here we have the values in the table, where we also would need to state that there are some numbers that are strike through, and these are still calculated, but we cannot take them into consideration because there were some technical problems during this cold recovery season time. But we have their values for, let's say, 3 houses. And here we can also see that the monitored effectivity of cold recovery is between 3.9 and 2.7. And this also means that the value, or the additional value that we are providing with this cold recovery during the ventilation or with ventilation system, is a very good result and is adding additional value to the system. And here again, when we make this comparison, we have to consider this total cold recovered, that it depends on the outdoor climate, flow settings, and comfort settings. And in that way, if we have a high outside temperature, and we do not just want to take that high temperature inside of the house, we will recover the cold from the indoor air. And then by that, we are reducing the outdoor temperature that is then delivered to the house as a supplier. And there was also in the questions section before a question that we can still have balanced ventilation without energy recovery. And this is something that we are calling ventilative cooling. For example, if we are closing the bypass flaps for our comfort Q units, then there will not be any energy recovery, because the one side of the exchanger is used for supply air and the other side is used for the extract air, so there is no possibility to recover any energy. And by that, we can use it as a passive cooling solution for the houses and for the system. In a way, for example, in the summertime, that in the nighttime we are cooling down the house, without any energy recovered. And that's also a good opportunity to have a technically advanced solution to use, let's say, our environment to help to provide better indoor solutions. Here, it's again, when we are checking the numbers in the table where we have fan consumption, ventilative cooling, and also seasonal performance factor for this ventilative cooling solution, that this effectivity is rather high, and we can create good solutions with that. For example, if we take again this idea that we are cooling down the house in the night time, then in the morning we have a nice fresh air inside of the house, and we can start with our day with this good air. And also during the night time, we are able to have better sleep quality if the conditions are better there. But here again, we need to think about if this data has been collected by the Central Europe solutions, and we need to consider the outer climate and the temperature and humidity, flow settings of the system, and also comfort settings of the system. For example, where we have set the temperature. Is it rather cool or warmer? And this is also something that is calculating for the unit to open the bypass in a modulated way, or then how to control the airflows in the unit. And also what is interesting here to see is that total ventilative cooling is relatively high when ground-free cooling is used. That we can see that those kilowatt hours for this thermal energy are significantly higher than for the systems without this ground preheating or pre-cooling, sorry. And this, in that way, also we are getting better indoor climate for us in the summertime, and this is an advantage because we are then taking the energy back to the ground as well with this solution. So we are using what the environment is giving us in the most clever way. Yes, and if we had the opening question in the beginning of this session, is that how much energy is saved by a balanced ventilation system compared to ventilation via windows, then here is a nice graph where we can see how the building construction and building sector has evolved and how the technology has advanced during the years, with transmission losses and ventilation losses in different decades. That for example, in 1940s, we had transmission losses for the house around 230 kilowatts per hour per cubic meter per year, and ventilation losses around 50 kilowatts per hour. And with time, the heat loss are reduced because we are building more airtight houses and we are using more insulation, and the materials that we are using are getting better. And nowadays it is that the transmission losses and the heat losses for ventilation are more or less equalizing. But if we are having our ventilation systems with heat recovery around 90%, this in the end is affecting our overall heating costs or savings for our heating costs up to 50%. So, and this is a very high portion. If you think about it, then if we can reduce something by half, this is a significant financially and also for the comfort as well. For cooling, on the other hand, it is difficult to calculate a specific number. What would be the costs for the cooling that is recovered, since there are more variable conditions there. Let's say humidity plays a huge role, and also air volumes, and that is a little bit more difficult to give concrete answer on that. Yes, but overall, let's say that with the heat recovery around 90%, we could save up to 50% on the heating side. And to summarize this session, there is that balanced ventilation systems are effective for heating and cooling costs for residential buildings. We could set our systems in a way that we will take the most of the technology and therefore save some costs when we have a system that is built for considering all the seasons. Installed capacity of central heating cooling systems can be reduced when combined with balanced ventilation system. And balanced ventilation systems can provide ventilative cooling in an effective way for a comfortable supply of fresh air, especially when combined with ground heat exchange. So in that way, let's say when the main focus for ventilation is to exchange the air inside of the house, then while using right technology and right features, we could widen that idea and to provide additional value to the system without adding, let's say, additional cooling devices to the residential buildings. And that would be all for the moment from our side. So thank you everybody who participated. Thank you also for the questions that we have had so far. Are there any other questions coming up based on the information and the slides?
Yeah, there's a question. When unit senses high indoor humidity, is this in default settings or is this an advanced setting? So, as I already mentioned, we have these integrated sensors measuring the humidity, and if they recognize the humidity is too high inside, the unit will rise the air volume flow. So, but this is an optional setting that you need to set during commissioning. That's not standard, but it is possible to do it. And we also have external humidity sensors, which can be installed, for example, in the bathroom. And if that bathroom sensor detects a high humidity, the unit will also increase the air volume flow. If you have any other questions, please use the chat session and we can answer your questions. Yeah, so there are no more questions. So Piret, I think we can close this session now.
Yes,
You can
but
also contact us after the webinar. You have our email address, so feel free to contact us. Thank you for watching the webinar, and yeah, have a nice day. Goodbye.
thank you. And as Adrian mentioned, then if there are some additional questions coming up, or for example, if you feel that the answers that were presented in the beginning were not answered, and there would be a need for some additional information, then as well, please let us know, and we will do our best to answer the questions in a more technical or more depth way. And therefore, yeah, feel free to contact us if you have any further questions or some suggestions or comments. Thank you also from my side. And if there are no questions for the moment, then thank you again and wish you a very good day.
Thank you. Goodbye.